Welcome to the final video on gas laws. So today we're going to be doing some gas stoichiometry. Okay, so to start this up, I want you to think about the combustion of methane. All right. Now I want you to pause the video and see if you can get the chemical equation for the combustion of methane. And I'll give you a little clue here. Methane is CH4 gas. Okay? So hopefully you remembered that methane is a hydrocarbon, and combustion means reaction. Combustion of a hydrocarbon means reacting with oxygen to form carbon dioxide and water vapor. Okay, so I'll balance this like so. All right, so now I want you to pause the video here, and I want you to come up with a list of all the things that you know these coefficients mean. Okay, go. So far we have a count of molecules. So one molecule CH4 reacts with two molecules O2, yada, yada, yada. We also said that this is moles. Okay, 1 mole of CH4 reacts with 2 moles of O2. Now I want you to use Avogadro's law. And pause and think if you can come up with Avogadro's law, which is V is directly proportional to the number of moles. All right, so if I say that 1 mole of methane gas reacts with 2 moles of oxygen gas, as long as they're under the same sets of conditions, you can also say that 1 volume of CH4 can react with 2 volumes of oxygen. Okay? The units don't really matter as long as they're the same. So I could say like 1 liter of CH4 reacts with 2 liters of O2 as long as everything's under the same conditions. I could say 1 milliliter of CH4 reacts with 2 milliliters of oxygen. All right, so you just have to be consistent. So we're going to use that at some point today. And I want to continue a little bit more with Avogadro's law. All right, so the fact that volume is directly proportional to N. Now let's take a look at the ideal gas law. If volume is directly proportional to the number of moles. So volume's changing because number of moles is changing. That means the pressure is a constant and the temperature is a constant. So as long as pressure and temperature are constant, the number of moles is directly proportional to the volume. Now, one of the things that Avogadro found is that the volume of 1 mole of a gas is always the same. It doesn't matter what kind of gas it is. The volume of 1 mole of a gas is always the same. So he found that 1 mole of a gas equals 22.4 liters of gas at STP. Okay? So this is called the molar volume of a gas, kind of like molar mass, all right? We will use this. Hopefully you see that it's set up as an equality, which means we can make conversion factors out of it, all right? So like I said earlier, we're going to be talking about stoichiometry today, stoichiometry using gases. So they come in 3 flavors. There are easy problems, there are medium problems, and then there are longer problems. Okay? Here's an example of an easy problem. Okay? So this is actually handily enough. Uses the same chemical reaction. 29 liters of methane undergo complete combustion at some pressure and temperature. How many liters of each product would be present at the same temperature and pressure? Okay, great. So I can set up my equation. Yields CO2 plus H2O. And I can balance it by putting a 2 here and a 2 here. All right, these are both gases. Now, here's the key phrase here. At the same temperature and pressure. Okay? As long as the temperature and pressure are the same, remember we can just use gas volumes. So this is the easiest type of problem because we don't really need any of this information. I can set up simple conversion factors, simple dimensional analysis. So question mark, I'm going to keep it in the same units. Question mark liters, start with CO2, equals 29.0 liters CH4. Okay, and because we're under the same sets of conditions, I can just use gas volumes as my conversion factors. So I know that 1 liter of CH4 will make 1 liter of CO2. So I get 29.0 liters CO2. Because my liter CH4 cross out, I'll get my liter CO2. Now I can also do water the same way, water vapor the same way. 29.0 liters CH4 times 2 liters water, 1 liter CH4. Okay, and I'll get 58.0 liters H2O. All right, nice and easy. So if all your gases are at the same temperature and pressure, keep it simple and just use gas volumes as a conversion. All right, here's the next harder one. All right, now I don't have, so if 2.32 grams of magnesium is reacted with excess hydrochloric acid, what volume of hydrogen gas at STP will be released? Okay, so again, at STP. That's going to be the key here. So the first thing we need to realize is that my given, okay, is not the same as my wanted. So my given is magnesium, my wanted is hydrogen gas, which I know at some point means I'm going to need to use mole ratios. All right, awesome. So that means that I need the balanced chemical equation. So magnesium, which is a solid, reacts with HCl. And hopefully that you remember that this is a single displacement reaction. It makes magnesium chloride, which is MgCl2 aqueous, plus hydrogen gas. All right, now I need to balance. So I need to put a 2 in front of the HCl. And then I'm ready to go. All right, so I just kind of want to think about a plan here, okay? Now, the key here is that the hydrogen gas is at STP. And if you see a gas at STP, you should be thinking molar volume of a gas. And I'll give you bonus points if you say it like that in class because I'll laugh hysterically. All right, so I know that I can get to liters of hydrogen gas from moles of hydrogen gas and I can use molar volume to do that. Okay? Now, where am I going to get moles of hydrogen from? Well, my given is magnesium, and I'm given grams of magnesium, so it's easy enough to go from grams of magnesium to moles of magnesium, and then moles of magnesium, okay, moles of magnesium to moles of hydrogen. This is all stuff that you did last chapter. Okay, now, molar volume is a conversion factor, which means I can do this whole thing in one-dimensional analysis step. It's not always going to be the case, so it's a good thing to write this kind of step out, all right? So I'm just going to keep filling in all the conversion factors that I need because I think this is really helpful. So this is molar ratio, okay, and this is going to be molar mass. All right, so question mark, liters, H2 equals 2.32 grams magnesium. All right, so I'm going to put my grams magnesium on the bottom, my moles magnesium on the top. This is a molar mass, so it's 24.305 grams magnesium for 1 mole magnesium. And then I'm going to put moles magnesium to moles of H2, 1 to 1, okay, 1 to 1. And then I'll do my last conversion factor, which is the molar volume of the gas. So I'm going to put 1 mole H2 on bottom, okay, to cancel my moles H2, and 22.4 liters H2 on top. Okay, so my grams magnesium go away, my moles magnesium go away, and I'm left with liters of hydrogen, which is what I want. Okay, when you do the calculations, you should end up with 3 significant figures. So it's 2.14 liters of hydrogen gas. All right, so this is sort of the medium difficulty problem where you're given your gas at STP. So either your given is a gas at STP or your wanted is a gas at STP, or both. Okay? Now here's our next one. And this one is difficult. Okay? It's going to be very similar to the last one. So let's take a look. Phosphine, pH3, is the phosphorus analog of ammonia, NH3. It can be produced by the reaction between calcium phosphide and water according to the following equation, which is of course not balanced, and I didn't leave enough space in there, so I can do that real quick. What volume of phosphine? All right, so here's what I'm looking for. Here's my question mark. And I'll probably put this in liters because that's probably the easiest one to find. That's what we're looking for. Measured at 18 degrees Celsius and 102.4 kPa, is produced by the reaction of 8.46 grams of calcium phosphide. Okay. So here's some more. Here's my given. Now, I'll notice again that my given compound is not equal to my wanted compound, which means at some point I'm going to need to do a mole ratio. So keep that in mind. So I guess that means the best place to start is to balance the equation, since we're going to be doing mole ratios and whatnot. 2, 3, 6. All right, now the unfortunate thing here is our gas is not at STP, which means no molar volume of a gas. And we'll put a little frowny face. Okay, if you can't use molar volume of a gas, you need to do ideal gas law. All right, so that's PV equals nRT. All right, so I'm given the pressure, 102.4 kPa. I'm trying to find the volume. I'm not given moles, okay? So that's another thing that I need to find. I'm given R as a constant, and I'm given the temperature. So in order to find the volume of phosphine, I need to find the number of moles of phosphine. So here's how I'm going to plan this out, all right? I want liters of phosphine. That's my end product. All right, I am going to get that from moles phosphine. And to do it, I'm just going to use ideal gas law to convert from one to the other. Okay, well, where am I going to get my moles phosphine? I'm going to get that from moles Ca3P2. And what conversion is that? You betcha, it's mole ratio. Sorry about all the you betcha. I went to school in Minnesota. Give me a break here. My moles calcium phosphide is going to come from my given, the grams calcium phosphide. And I will use molar mass for that. All right, so here's my plan. Now, here, all of these, this is all dimensional analysis. Okay, this is an equation. So what I'm going to need to do is I'm going to need to solve a dimensional analysis to moles of pH3, and then I'm going to need to plug those moles of pH3 into the ideal gas law to solve for the volume. Okay, so let's start going. So I want question mark moles pH3 equals my given, which is 8.46 grams calcium phosphide. And then I'm going to put my grams calcium phosphide on the bottom. Okay, and I'm trying to go to moles. This is molar mass, so I just use the periodic table. I get a molar mass of 182.18 grams calcium phosphide and 1 mole calcium phosphide. Okay, and then I need to go moles of calcium phosphide to moles of pH3. Okay, those numbers is mole ratio, so they come from the balanced chemical equation. So it's 2 moles of pH3 to 1 mole Ca3P2. All right, and then I get 9.29 times 10 to the minus 2 moles pH3. Now, I'm not done with the problem, so I'm not actually going to round this value, right? I'm going to use the whole decimal when I get to the next step, okay? The next step is, now that I have moles pH3, is to use ideal gas law to go to volume of pH3. Okay, so I'm going to need a little bit more space here. So do this just like you have before. Divide both sides by pressure and say volume equals nRT over P. I always start with R, and it's on top, 0.0821 liters times atmospheres over moles times Kelvin times my temperature in Kelvin. All right. Temperature is 18 degrees Celsius, so that's 291.15 Kelvin. So that's temperature, there's R, I need the number of moles, which is 9.46 0.29 times 10 to the minus 2 moles pH3. Okay, that just comes right here. And again, I'm going to use the whole value. And then the bottom is the pressure. And the pressure is given as 102.4 kPa. Okay, now, important step here. Check your units. Okay? So my kelvins cross out, my moles cross out. Uh-oh, I have atmospheres in here and kPa in here. So I'm going to need to do kPa on top and atmospheres on bottom. And you should be able to find that 1 atmosphere is 101.325 kPa in 1 atmosphere. All right, then I just do the math, all right, and in order to figure out sig figs, I kind of need to work backwards, right, because this has a bunch, this has a bunch, this has 4, and this is defined, okay? So it's really going to be limited by this number, which is going to be limited by this number. So we're looking at 3 sig figs, which is 2.20 liters of pH3. All right, so this is a beast of a problem, okay? There's a lot of stuff going on here. So you want to work through these slowly and methodically. All right, the big tricky one here is this last step where you have to convert between atmospheres and kPa. All right, that's the kind of tricky part of this problem. Everything else you know how to do so far. All right, it's just kind of putting everything together. So that is the lesson on gas stoichiometry. Good luck.